In this video, we'll talk about the interactions between molecules and ions in our body. It's really no different than how animals or human beings interact with each other. People have different personalities, different backgrounds, allowing some to get along better with others. Fortunately or unfortunately, the ions and molecules in our body have a more seamless approach to getting along. So we'll see how that works. It is currently Sunday, June 7th, 2020. Protests are going on across the world now. My name is Matt Halter, and I just want to give you my 2 bits on Donald Trump, our president. You can hear more on my podcast, which I don't have. So once I have it up, which I won't, you can hear it there. It's not about politics, and certainly I don't agree with much of his politics, but being that we live in a representative democracy, we are subject to who's ever our presidents or in office. It's really how he treats human beings. He degrades people, he calls people losers, lowlifes, what have you, and the list is endless. A constant barrage of inflammatory remarks against individuals that he doesn't like. And his job is not necessarily to like people, but his job is to treat people with respect, being that he's the leader of the free world, or theoretically the leader of the free world, which we're all questioning at this point in time, because not everyone has the freedom, as much freedom as they would like, or as much freedom as other social or economic groups of people. So I just want to throw that out there. We will move on to chemical interactions, which are a lot easier to explain. So the first thing we need to talk about is water, because our body is composed of roughly 60% water, give or take, depending on what literature you read, what research you're looking into. But our body is predominantly water. And the makeup of water is going to dictate how things are interacting with each other, or more specifically, interacting with water. Water is both a molecule, as we see on the upper left here, that is H2O. But water is a substance. So, for example, this glass is filled with the substance we know as water. So when we are referring to water, we could be referring to the substance. Generally speaking, though, within physiology, we're talking about the water molecule. And the water molecule is composed of 2 hydrogen atoms and 1 oxygen atom, and they are bound together via covalent bonds. And covalent bonds are the sharing of electrons between atoms. So in this case, this oxygen atom right here is sharing these purple electrons with this hydrogen. This oxygen is sharing these 2 electrons with this hydrogen atom. That is a covalent bond. But not all covalent bonds are created equally. Anytime we have a molecule with oxygen and hydrogen, we get a little bit different makeup of the covalent bond. There's still an equal distribution there's still sharing of electrons, but there's an unequal distribution of electrons. Because oxygen is very electronegative, it pulls those electrons toward. If we see carbon and hydrogen bound to each other, we don't see the unequal distribution here, because carbon and hydrogen have the same electronegativity. But ions like oxygen and nitrogen and some others are super electronegative. So when they're bound to hydrogen and to a certain extent carbon, they will pull those electrons closer to themselves. So that's what we see right here. And by doing this, the water molecule creates partial positive charges. Because those electrons are being pulled closer to oxygen, it imparts 2 partial negative charges on the oxygen atom and individual partial positive charges on each hydrogen atom. This molecule is still neutral because those 2 partial negative charges that we see up here are going to cancel out these partial positive charges. But it is what we refer to as a polar molecule. And it is polar because it has different characteristics on each end of the molecule. On this end, it's partially negative. On this end, it's partially positive. Water is a polar molecule, but it is neutral. So, a number of polar molecules in the body, it's an endless list. But here's two significant polar molecules. Water, as we discussed, and also glucose, which we will talk about nearly every lecture during this semester. Glucose is a polar molecule, and it's a polar molecule because, as we see, there's a lot of oxygen atoms bound to hydrogens. And that's going to create a lot of polarity in this molecule. But we also have nonpolar molecules. Nonpolar molecules tend to be lipids, such as fatty acids, triglycerides, steroids. And they tend to be made up predominantly of carbon chains with a bunch of hydrogens on them. So one thing we don't see here is at each vertex or vertice in this chain, that represents a carbon atom. And if we just look right here, a carbon atom always wants to have 4 bonds. So we see one bond right here. We see another bond right here. But the way this is drawn, and this is often how it's drawn in chemistry and biochemistry, there are some assumed hydrogen atoms coming off of this carbon. So that would create the 3rd and 4th bonds. But the significance of this is we have a carbon chain bound to a bunch of hydrogen atoms. Carbon and hydrogen are not very electronegative with respect to each other. So there's no polarity built into this molecule. Certainly there's going to be a certain degree of polarity over here with the hydroxide, but by and large, this fatty acid is going to be characterized by the non-polarity of this side chain right here. Okay, so we have polar molecules and we have nonpolar molecules. The long and short of it is polar molecules will enjoy hanging out with each other, and nonpolar molecules do not, and nonpolar molecules enjoy hanging out with each other. I will restate that. I'm not sure I said that very clearly. Polar molecules will hang out with each other, but don't like to hang out with nonpolar molecules. And the converse is true as well. Nonpolar molecules will freely interact with each other, but they don't interact well with polar molecules. So what we see in the upper left here is this term hydrophilic. And that is water loving or attraction. There's a great attraction to water. Polar molecules are hydrophilic. In this slide, what we see is polar molecules are hydrophilic, meaning they have a great attraction for water, and they are lipophobic, meaning they have a fear of lipids or nonpolar molecules. The converse is true. Nonpolar molecules tend to be lipophilic. They have a great attraction for other lipids or other nonpolar molecules. Nonpolar molecules are also hydrophobic. They have a fear of water or a poor interaction with polar molecules. So if something is hydrophilic, they're going to be lipophobic. If a molecule is hydrophobic, they will also be lipophilic. And these characteristics are going to dictate how ions and molecules and cells interact with each other. There are some molecules, like this phospholipid right here, which have regions that are polar, and they have regions that are nonpolar. We call these molecules amphipathic molecules because they have a polar region and a nonpolar region. This phospholipid has this green phosphate head and lipid tails. Keep in mind, lipids are nonpolar, as we looked at in a previous slide. The phosphate head here is going to have a positive and negative charge distributed on different ends of this green head, making it polar. So we do have amphipathic molecules that have both characteristics. Now, a really good way to illustrate how a phospholipid or an amphipathic molecule is going to interact with the body is this image right here. We have thrown that phospholipid into a glass of water. And we didn't specify to the phospholipid how we wanted it to orient. But immediately the head stuck in the water and the tails are sticking directly out of the water because the tails are hydrophobic. They do not want to interact with the H2O. This slide right here, we see a cell. We see 3 cells, but they're all representing the same thing. In the bottom left, we see a cell, and this is generally how I draw cells because drawing a circle is super quick. If I was going to do this super accurately, I would draw 2 circles because our cells are composed of a bilayer, 2 layers. And if I want to even elaborate more, the best depiction is the one in the upper right here. Our cell membranes, otherwise known as plasma membranes, are composed of the phospholipids that we just talked about, those amphipathic molecules that have a polar region, which is the green heads here, and a nonpolar region, which are the pink tails. In our body, like I suggested at the outset of this video, our body is mostly water. Outside of cells, we have a bunch of H2O. Inside of cells, we have a bunch of H2O. And that is going to influence how these phospholipids orient in the plasma membrane. The lipid tails are always going to be facing away from the water. So we have this inner membrane here, which is represented right here, where we have the phosphate heads facing the H2O. The phosphate heads are polar, water's polar, so they get along with each other. The same is true on the outside where we have water, and these phosphate heads are interacting with the water. In both cases, we have the lipid tails occupying the interior of this cell membrane. And the composition of the cell membrane is going to dramatically influence what enters a cell or what exits a cell. How things get into cell. Are they getting in passively with no help, or do they require a channel to get into the cell? And we will talk about that in subsequent videos. Thank you for listening. Happy Sunday.